Hello again, Mr. Wakefield here, looking at section 4.6, the last section of chapter 4. We're going to be talking about kind of a new thing here today. There's some similarities with the rest of the chapter, but mostly new. Our topic today is functions, okay? And let me start out by defining three words here that'll help us understand functions better, and then we'll actually talk about what a function is. First of all, any set of ordered pairs, that's called a relation. Any set of ordered pairs. So, for example, down here at the bottom of the page here, you can see that they put a set of 5 ordered pairs in a group here, and that's why they got these fancy brackets here at the end, at the front and at the back of the problem here. Okay, those brackets mean that they're putting a bunch of things into a set. In this case, they're putting a bunch of ordered pairs into a set. So this is called a relation because it's just a set of ordered pairs. Same thing as with this one. There's 4 ordered pairs here, and there's 5 ordered pairs here. Okay, so a relation they both are. All right, now, within that idea, and this will get us started on that first problem, the set of all x's, x coordinates in other words, in a relation is called the domain. And so this might be the simplest problem you do all semester. Okay, when you have just a simple little list of ordered pairs and they ask you for the domain, all you got to do is just tell me what all the x's are. And you don't have to do any duplicates, okay? So see how 3 appears twice here as an x value? Okay, you don't need to say it twice. Just tell me all the different ones when you do the domain. So 1, 3, 4, and 9. If you do happen to say 3 twice because it appears twice, that's not wrong. It's still the same correct answer. I'm just saying that you don't need to say it twice. You just need to say all the different ones that are all the different ones that represent x values. That's what the domain is. Then the next word here is range. It's exactly the same thing as the domain, except for it's the y's instead of the x's. So in other words, you take all of the y values. Again, very simple problem here. There's no math really to do here. You're just making a list. Okay. So 3, 4, 2, 5, and 1. 3, 4, 2, 5, and 1. Okay. And put commas in between them. Okay. You're not, again, there's no math here. You're not adding them. You're not subtracting them, anything like that. Just put commas in between them, because that's what you do when you make a list, okay? The last question that they ask us after they ask us to identify the domain and range, it says determine if the relation represents a function. So now is a good time for me to talk about what a function is. Let's go back up to the top. Okay, it says a relation in which each x corresponds to one and only one y is called a function. When I was a student taking a similar class as this one that we're taking here, Math 51, when I first saw this definition, I thought it was kind of confusing. Okay, it took me a while to kind of get it. And so what I did here was I wrote down a couple more sentences that I think will help you get it better. Okay, in other words, a function is what? It is a set of ordered pairs in which no 2 different ordered pairs have the same x. Okay. If a relation has 2 different ordered pairs that have the same x, it's not a function. Okay, if all the x's are different, then it is a function. If all the x's are different, then it is a function. Okay, if you have 2 different ordered pairs, look over here for example. See how you have 2 different, I'm sorry, that's the wrong one. I meant this one right here. See how you have 2 different ordered pairs right here with the same x? Okay, these 2 ordered pairs both have x equal to 3. If you have 2 different ordered pairs that have the same x, then that's not a function. All the x's have to be different for all the different ordered pairs that you're looking at in your relation here. Okay, so and again, it doesn't matter, the y's don't matter when it comes to being a function. The y's do not matter, and so it's okay if the y's are the same. That makes no difference. So see how over here the y's are the same on a couple of ordered pairs? That does not affect whether or not it's a function. Okay, so what I was going to say here was function yes or no, and we're going to circle no, all right, because it's not. And again, why is that? It's because these 2 numbers right here tell us that we have 2 different ordered pairs with the same x. All right, can't have that if you want to have a function. All right. Whereas over here, as long as we're on the topic, I'm going to answer the function part of the question first. I'll get back to the domain and range in a minute. Okay, is this a function, yes or no? Well, it is a function this time, and the reason why is because all of the x's are different. Okay, if all the x's are different for all the ordered pairs in your relation, then that means that it's a function. Okay, and that's how it works. All right. What's the domain and range now to finish off this problem? The domain is all the x's, -4, 4, 2, and -2. Okay. So list that out. Put commas in between them because it's just a list. We're not doing any addition or subtraction or multiplication or anything like that with those numbers. Then the range is all the y's, 1, 7, and then you don't need to say the same one twice, and then 8. So you just need to say 1, 7, and 8. But again, if you say the number 7 twice, it's not wrong. It's not wrong to do that. It's just that that's not normally how it's done. How it's normally done, like I said, with both domain and range, you just list out all the different numbers, okay, that are going to be x's if you're doing domain, or are going to be y's if you're doing the range, okay? So that's domain, range, and function. Now, when I give you a graph, and remember you guys, you might be wondering, wait a second, all right, the directions are still the same here. We don't have a new set of directions for C, D, E, and F, but yet the problems look completely different. They're graphs instead of just having a small little set of ordered pairs. That's not a coincidence, you guys. Please remember that when you have a graph, and yes, I know these aren't lines, okay, but these are graphs too, all right, and we put them on an x-axis, y-axis graph. Your graphs are not always going to be lines. All right, like I promised you in the early part of this chapter, I'm never going to ask you to graph anything. In other words, draw it yourself, unless it's a line, okay, or something very closely related to that. We'll see that later, but very closely related to that. So if you get something like this right here, it'll be something that's already given to you. These graphs are already given to you. So again, I'm just reminding you that lines are going to be the only shape that you're really going to be asked to graph in this Math 51 class, but sometimes you get some graphs already given to you as part of the problem, the original problem, that are not lines. So don't be surprised by that. Okay. So what do we do with these graphs? Well, please remember, you guys, and this is the key thing, graphs are relations too, because a graph has a bunch of points on it. And so it is a relation also. It's a bunch of ordered pairs, just like this right here is a bunch of ordered pairs. But the difference is that with the typical graph, you guys, including all these graphs here, there's an infinite amount of ordered pairs on this thing. Partly because the arrows tell us that it goes on forever in two different directions right here. So it's infinite. It just keeps on going on and on and on. Okay, but even in a problem like this right here that doesn't have any arrows, even this has an infinite amount of ordered pairs on it. Okay, the reason why is because if you look really, really close at this thing, okay, if you include all the little decimals in between the whole numbers here, all right, for example, this point right here, it looks like it is 1, 2 right here, right? And then this point down here is 2, 0. All right, there's, believe it or not, you guys, there's an infinite amount of points between that. Let me zoom in there so you can see it better. There's an infinite amount of points in between those 2 points right there. Okay, why? Because of all the decimals. Okay, there's an infinite amount of decimals just between y equal to 0 and y equal to 2 right here. Y equal to 1.1, y equal to 1.2, y equal to 1.2736. I mean, you could go on forever and ever with all the different decimals that are just between 0 and 2 right there. So even this thing has an infinite amount of ordered pairs if you include all the decimals, and you do have to include all the decimals. It's not just the whole numbers and stuff like 0, 1, 2, 3, that kind of thing. Okay, so my point here, you guys, is that even the graphs that don't have arrows on it, okay, even those have an infinite amount of points. So basically the typical graph is going to have an infinite amount of points on it. That's an issue here because up here we just had 5 ordered pairs or 4 ordered pairs. So it was real easy to just list out the X's and Y's real quick because you only had like 5 points or 4 points. What happens when you have an infinite amount of points? Well, you can't sit here and list out an infinite amount of X's. The list would just go on and on and on forever and ever off the side of the page and everything. Okay, so you can't do it that way. But here's the good news, all right? When you have what we call a continuous graph, which all of these are, and continuous graph just means that if you draw if you put your pencil over the graph from the left side of the graph to the right side of the graph, okay, your pencil never comes up off the paper. It just continuously moves through. It doesn't break at all. It doesn't stop and start again, for example. When you have a graph like that, and I'll never ask you to do one of these problems unless it was like that, okay, continuous. What happens is that you just need to know 2 numbers for the domain and 2 numbers for the range. Let me show you what those numbers are. Okay. Up here it says finding the domain and range of relation by looking at its graph. That's what we're doing right now, right? We're not looking at the small little set of ordered pairs. We already did those 2 problems. We're looking at the graph now. So what are the directions? It says for the domain, you're looking for the leftmost X value and the rightmost X value. I'll come back to the range in a minute. Let's just focus on the domain first. Leftmost X value, rightmost X value. Why are we doing that? Well, I'll explain that here in a second, but let's focus on actually figuring it out first. Okay? When you find and I'm going to start out with problem F first, by the way. We'll come back to the other 3 because the problems that don't have arrows are actually easier than the ones that do. You'll see why here coming up. But let's focus on this problem first. Where is the leftmost point, the point that's furthest to the left on this circle graph right here? Okay, it is this point right here, isn't it? That one right there? Okay, so here's what you do. You need to realize that domain is X, and so it's not enough just to find the leftmost point. You also need to find the X value there. Don't look for the Y value there because domain only is for X's, right? So what is the X value there? -1, -2, -3, -4, -5. So here's what I do. I put a -5 first. I put a comma. This is not going to be an ordered pair. Okay, I'm not going to use the brackets this time, although we'll see something similar to that later, but it's not an ordered pair. Okay, I'll explain what it is here in a second. But after you do the leftmost X value, by going to the leftmost point and finding the X value there, we just did that. Okay, we went to the leftmost point and we figured out that the X value was -5. Now you do the same thing, but you go to the rightmost point of the graph. In other words, what is the point on this graph that is furthest to the right on the graph? It is this point right here. Okay, this point right here. And so we don't want to just take that point and say, hey, that's the answer. No. What is the X value there? Because again, domain is not, it has nothing to do with Y's. It's just X's for the domain. So isn't the X value there 2? 1, 2, okay, and then 3 and 4 are past that. So X equal to 2 is at the rightmost point of the graph. So we put the 2 there. Okay, so we got these 2 numbers, right? How in the world is that suddenly become the domain? Well, as we'll learn more later, this is a kind of a simplified version of something called interval notation. But what interval notation means is this. It means that if you put 2 numbers down with a comma in between it, again, not an ordered pair. I know it looks like it, but it's different when you do interval notation. And it says up here, write your domain and range in interval notation in the problems that have graphs. So that's why I'm doing this. Okay, but for interval notation, if you've got 2 numbers with a comma in between it, it means that your domain is every single number in between -5 and 2. Every single one. That includes all the decimals. Okay, so some of you might be thinking, hey, wait a second, -5 and 2, why don't I just list out all the numbers between -5 and 2? I'll say -5, -4, -3, -2, -1, 0, 1, 2. Hey, I've got them all, right? No, you don't. No, you don't. Because you forgot about all the decimals in between. How many decimals are there in between these 2 numbers? An infinite amount of them. Just like I said earlier, there's an infinite amount of decimals in between 0 and 2. Same thing here. So you can't just list them out when you have a graph. You can't do that. Okay? So you take the point that's furthest to the left and the point that's furthest to the right, and because it's a continuous graph, every single number in between -5 and 2 will have its own x value on here. Will have its own point. For example, x equal to -4, that has a point. Since it has a point right there, that means that -4 is in the domain. Okay, x is equal to -4.5. That has a point here. It's right about here. Okay, it's kind of hard to see there because it's a decimal, but it's there. Okay, and the point is, though, is that if you take the leftmost x and the rightmost x, every single number in between will be in the domain. I guarantee it. Okay, so all you have to do is find that leftmost x value and the rightmost x value. Okay, and just put a comma in between it because that's how you do interval notation. And then that will mean, when you see that comma, it will mean that every single number in between -5 and 2 is in the domain. And that's exactly what the answer is. Every single number between -5 and 2. The range is similar, but because the range is y, we're focusing not on left and right. By the way, why did we focus on left and right when we did the domain, you guys? It's because the x-axis goes from left to right. Domain is x, so x-axis. It makes sense, right? Since the y-axis goes up and down, though, from low to high, that's why the range is lowest to highest. It's because the y-axis goes low to high. All right? And so what you do, same idea, only this time you take the lowest point and you take the highest point instead of the leftmost and the rightmost points. Okay? And because you're looking for the range values here, you got to focus on the y coordinates at those points, not the x's. What's the y value at this point down here at the lowest point? It is -1, -2, -3, -4, right? So that's what it says here. Lowest y value means go to the lowest point of the graph and then give me the y value there. That would be -4. Okay? Then it says give me the highest y value. Again, that means that we go to the highest point and then you just tell me what the y value is right there. 1, 2, 3, 4 on the y-axis here. So the y value there is 4, and that's your domain and range. Okay? So yeah, we'll see plenty more of these here coming up, but that's a good first problem to start with there. I'll show you how to figure out whether or not it's a function. We still got to do that too. The way you do that with a graph is different than the way you do it with just a simple small amount of ordered pairs here like we did in A and B. It's a little bit different. Okay, I'll get back to that in a moment, but I want to keep on focusing on this whole domain and range thing where you do the leftmost and the rightmost and the lowest and the highest. I want to keep focusing on that. But here's the thing though, you guys, on these other three problems, there's one other thing we need to consider before we get started with domain and range. We have to consider the fact that these graphs have arrows. That matters. Okay. All the arrows, I know some of them don't look like it, but I promise you, in all the domain range problems, the arrows will always be diagonal arrows, even if they don't look like it. Okay, meaning that they don't go straight up and down, even though it almost looks like it here, and they don't go straight across, they go diagonally like this. Same thing with this. It's going I know it's almost straight up and down, but it isn't quite. It's just diagonally, just very steep diagonal, but it's still diagonally here. When an arrow is diagonal, which again in the domain range problems they always will be, that means that the graph is going forever, because arrows mean forever on a graph, but it's going forever in two different directions at the same time. Here's what I mean. When you're going diagonal this direction, that means that you're going forever upward and forever to the left at the same time. Okay? So if you're going like this, you're going forever up and forever to the left at the same time. All right. This one, because it's going like this, that means it's going forever up and forever to the right at the same time. Okay, let me make that arrow a little bit more visible there. There we go. Forever to the right at the same time. Let me jump over to the other two problems just to make sure you understand these arrow things here. This one right here is going diagonal like this. It looks almost flat, like a horizontal line, but it isn't quite like that. It's still diagonal. So this one is going what? It is going forever up very slowly because it's almost flat, but it's still going up. See how my pen is still going up here? Okay. So it is still going up very slowly, but it's also going forever to the left. This arrow down here, not talking about the x-axis arrow there, that doesn't count. That's just part of the x-axis. But this arrow here that's part of the graph, that one is going forever downward very slowly. It's almost flat, but it is. See how my pen's going down? Okay, let me show it to you better here. It's going down very slowly, but see how it's getting further down the paper here? Okay, and it's also obviously going forever to the left, as I just showed you there with the pen. So, whereas this one here, let's do this last one here as well. This one is going forever upward, and forever to the right. Okay, so that's what's going on with these diagonal arrows. That's going to help us here. All right. Now, remember the domains always starts with the leftmost value, the leftmost x value. In other words, you have to find the leftmost point. What is the point that is furthest to the left on this graph? It is not this point right here because the arrow means that it keeps on going. It doesn't just stop right there. Okay, whenever you have one of these arrows, you know, like when you do this thing here where you do the two arrows for each diagonal arrow should have two arrows, okay, indicating what two directions it goes in. All diagonal arrows, again, have two different directions. Okay, so after you figure out what those two arrows are for each one of your diagonal arrows, all right, if one of them is going forever to the left, like this arrow is right here, then that means that there is no leftmost point. If something goes forever to the left, you guys, it's never going to have a leftmost point. You might be thinking, hey, what about if I just say like negative 1 million? No, when we say forever to the left, you guys, that means it's going to eventually pass negative 1 million. It's going to take a while, but it's going to pass it eventually. Okay? And so it's going towards infinite, it's going infinitely along, is what I should say. But because when we go forever to the left, because we're going in the negative x direction, remember, when you're going to the left, this is where the negative x values are over here. Okay, so if you're going forever to the left, that means that the leftmost x value, it doesn't exist because it just keeps on going on and on. It never stops at a leftmost point, like over here where this was the leftmost point here on this one. Okay, there is no stopping it. It's going to go to the left and it never stop going to the left. That's what this arrow means right here. So what is the leftmost point then? Does that mean there's no answer since there's no leftmost point? No, there is. It's just that since it goes on forever to the left, we call that negative infinity. Infinity because it goes on forever to the left. All right, so the leftmost x values, not that there is a leftmost x value, but they just keeps on going forever in that negative direction, and forever means infinity, right? But because it's going in the negative direction, the x values get more and more negative as this arrow goes further out, okay? As this arrow keeps on going forever to the left. And so the point is, you guys, is that whenever you have an arrow that goes forever to the left, because the x values are getting more and more negative, you know, negative 1,000, negative 2,000, negative 3,000, as this goes way, way out here, that means that it's approaching negative infinity. Not positive infinity, but negative infinity. So a forever to the left arrow always means that your domain, okay, instead of having a leftmost x value, you call the leftmost x value negative infinity. Okay? So forever to the left means that this is negative infinity, not positive infinity. I want to make sure we understand that, because when you go to the left, you're going in the negative x direction. Okay? Because the negative x values are on the left over here. On the other hand, you can see here that we have an arrow that goes forever to the right. Okay? So therefore, there is not a rightmost x value because it never stops going to the right. It keeps on going. Yes, it goes past x equal to 1 million. It goes past x equal to 1 billion. When it goes on forever, it passes everything, no matter how big the number is. There is no rightmost x value. And so it's also infinity. Put your comma here like we always do, in between right and left. But instead of it being negative infinity, this time it's going to be positive infinity, because when you go to the right, where are you pointing? You're pointing in the positive x direction. The positive x values are over here on the right-hand side of the x-axis. So to the left, if it goes forever to the leftmost is negative infinity. If it goes forever to the rightmost is positive infinity. And it's all because the signs are all because left is the negative x's, the right is the positive x's. That's why this one's negative, but this one is positive. Okay, now, that's the domain. What about the range? The range starts with the lowest point. Okay, there is actually a lowest point here. We don't have an arrow. You don't have an arrow here that points downward forever. Okay, if you did, like on this problem here, then there would be no lowest point. If it keeps on going lower, 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 then there is no lowest point. If it goes down lower forever and ever and ever, like this one does. We don't have that here. There is no arrow that goes straight down forever. And so there is a lowest point. It's right here. And since we're doing the range, you figure out what the lowest y value is, and that is -1, isn't it? Isn't that -1 right there, y? Again, don't look at the x. The answer is not 2. That's the x value. We're doing the range, so it's got to be -1. The lowest y value means you go to the lowest point, just like I did with the circle over here, okay, and then identify the y value there. Is there a highest point? That's the next thing you got to do here. Is there a highest point? No, there's not, because whenever you have an arrow that goes upward forever, that means that there is no highest point. It's going to pass every single point as it keeps on going up and up and up. So there is no end to it. All right, there is no highest point. If you say that there's a highest point, that must mean it doesn't keep on going past that. Well, when it goes on forever, that means it passes everything. So if you have an arrow that goes forever upward, we actually have 2 of them, but if you have at least one of them that goes forever upward, that means there is no highest y value. So it's either got to be infinity or negative infinity, doesn't it? Okay, because it goes on forever. Which one is it? Well, because the y values, because the positive y values are up here, whereas the negative y values are down here, when you're going upward forever, it's going to be positive infinity. Okay. If it goes forever downward, then the lowest point will be negative infinity. I'll get to that in the next problem here. Okay. But that's the range. Speaking of the next problem, let's get to it. All right. Is there a leftmost point? No, because we have actually not just 1 but 2 arrows that go forever to the left. If you have 2 arrows, or at least 1 arrow that goes forever to the left, that means that there is no leftmost x value. Okay, it goes forever. So the question is when it goes forever, it's going to be either positive infinity or negative infinity. Which one is it? Well, again, when you're looking at the leftmost x value, you're over on the negative side of the x-axis, aren't you? Okay, you're pointing in that direction anyway. And you're over there in this case as well. But you are pointing in that negative direction because the left side of the x-axis is like that, okay? It's the negative side. And so that's why, just like in the last problem, if the arrow goes forever to the left, the leftmost x value will always be negative infinity in that case. It didn't go forever to the left over here in problem F. That's why we didn't have negative infinity right here. Here, because of these left arrows for both of these problems, that's why the leftmost x value was negative infinity. Okay. Is there a rightmost x value? Is there a rightmost point? Yes. There it is. Okay, see how there's no arrows that go forever to the right? Okay, but this is the rightmost point. There's no points over here at all. There's no arrows that are pointing towards this direction over here at all. Okay, this is definitely the rightmost point. Okay, and by the way, in case you're wondering, okay, if you have arrows on a graph that they give you, okay, those arrows are never going to turn around. Okay, you don't have to worry about trying to figure out if this arrow is somehow going to turn around. If you're wondering, gee, is this a trick question? Is it possible that this could turn around? You don't need to worry about that. Whenever I give you a graph in the original problem and you see arrows, okay, I promise you it's not going to turn around from that. I'm not trying to trick you here, okay? It's going to keep on going in this direction. That's why this is the rightmost point. This graph is never going to turn back around and come over here somewhere, okay? This is as far to the right as it's ever going to get on this problem, okay? So if you have no arrows that go forever to the right, we don't, none of these do that, then there must be a rightmost point, and clearly this has got to be it. Okay, there's nothing to the right of that. So what is the x value, since we're doing the domain? What is the x value here? It's 0, isn't it? We're not looking at the 3, that's the y value. Okay, just the x value. How about the range? Range has to do with what? It has to do with the lowest point and the highest point. Well, we can see here that there is a arrow going forever downward. That means there is no lowest point. And we can see that there's an arrow that goes forever upward. That means there's no highest point. It keeps on going past everything. There cannot be no highest point. So that means that both the low and the high, both parts of the answer and the range are going to be infinite. The question is which one's negative and which one's positive? Well, the lowest y value, which always goes first, okay, make sure the left always goes before the right and the low always goes before the high. That's just the way it's written, okay? I'm not going to mark off a bunch of points if you reverse that around, but I will mark off a little bit because that's the right order to write it in. So don't forget that, okay? But the low goes first, and since there is no lowest point, we know it's infinite, but because as I mentioned a few minutes ago, because we're pointing down towards the negative part of the y-axis here, the positives are up here going upward, right? The negatives are down here going downward. That means that the lowest point, when it's infinite, going forever downward, it's not going to be positive infinity, it's going to be negative infinity. So we know it's infinite because it goes forever downward, but we know it's negative because it's pointing in the direction of the negative y values. Likewise, this one is infinite because it goes on forever, and this indicates that there is no highest point, like I mentioned a minute ago. But because it goes forever upward, it's going to be infinite. But because it's pointing the same direction as the positive x value is going upward here, the positive y value is going upward here, then that means that it's going to be positive infinity. And so that's problem D. Moving on to problem E here. There is actually a leftmost point here. Okay, I know that because what are my arrows telling me? It's telling me that it goes forever upward. That means there is no highest point. So that means that the last part of the range is going to be infinite. Okay, this part right here will be infinite because this is where the high part goes. Low and high for range, right? So since it goes forever upward, that means that the high part of the range is going to be positive infinity. Positive again because when you're going up, you're pointing in the positive y direction. Likewise, this is forever to the right. Remember, domain is left to right, so here's where the right goes, right here. Okay, here's where the right goes. Since it's forever to the right, it's going to be infinite, but it's going to be positive infinity again because it's pointing in the same direction as the positive x values. Okay, the negative x value or negative x values are pointing to the left over here, okay, as we talked about already. Now, because those are the only two arrows that go with this one diagonal arrow here, there's no other diagonal arrows, so there's no other there's no other arrows that go with that. Like I've been talking about, every diagonal arrow has two arrows that go with it. So since you got one diagonal arrow, you only got two of these arrows. Since it's only forever upward and forever to the right, that means that the left and the low part, they are not going to be infinite because there's no arrows pointing forever in those directions. So we will be able to find a leftmost x value and a lowest y value. Okay, these two things here, leftmost and lowest. All right. So what is the leftmost x value? You go to the leftmost point right here. See how there's no points over here, but further to the left than that. Okay, the arrows don't point in that direction either, so we know it's never going to go over here. Like I said, the arrows are not going to turn around. Okay, and so the leftmost x value is going to be -2 because this point right here is -2, 0. But we're only concerned about the x value when we're doing the domain. What is the lowest y value? Okay, well, what's the lowest point? Actually, it's the same point, isn't it? There's no points below that point right there. All right. The arrows don't bring us down there at all. Okay, so that's got to be the lowest point on the whole graph. What's the y value right there? It is 0. So 0 is the lowest y value. So now you can see how we do the domain and range. Okay, of course, let me know if you have any questions about that. But in the meantime, how do we do that part where we got to figure out if it's a function or not? Well, if you have a graph, you guys, if you're given a graph and they say, hey, is this graph represent a function or doesn't it? Okay, let me set it up here. The way you do that, though, if you look up about halfway down the page, all right, about halfway down the page, we got this thing called a vertical line test. A vertical line test, the reason why they use vertical lines is because as we learned in the previous video, this is from the previous video 4.5, if you have a vertical line, all the x's are always the same. If you have a vertical line, all the x's are the same. That's important here because, again, let me go back over here for just a moment. Let's start out with this one. Notice that if I put a vertical line right here, where does it go through? It goes through x equal to 1 right there. That means that all the points on that line have the same x. So if the vertical line hits the graph more than once, you can see that it hits twice right here at these 2 points that I'm pointing at. Okay? If it hits the graph more than one time, the vertical line, then that means that there are 2 different points with the same x. We can't have that with a function, can we? Okay? So if you have 2 different points of the same x, as we already determined, that means that that's not a function. So the vertical line test works like this. If you draw a bunch of vertical lines right here, okay, a bunch of vertical lines here all the way through the graph, all right, if it ever hits the graph more than one time, any of the vertical lines, it doesn't have to be all the vertical lines, it just, if there's even one time where any vertical line hits the graph more than once, then it's not a function. Because when it does, that means that there are 2 different points, or maybe there's even more than 2. Like I said, if it's more than once, it could be 2 times. It could have hit the graph even more than 2 times. But if it hits the graph more than once, then that means that there's more than one point with the same x value. And we know that you can't have that with a function if it's going to be a function. Okay, so the vertical line test says that if any vertical line hits the graph more than once, any of them at all, then you say no. Okay, on the other hand, if you go back over here, does any vertical line, as I draw a bunch of vertical lines through this to find out, does any vertical line ever hit the graph more than once right here? No, it doesn't, right? Okay, this vertical line hits right here one time. This vertical line over here hits the graph one time right here. Okay, they all hit it exactly one time. That means when all the vertical lines hit the graph exactly one time, okay, or in some cases they don't hit it at all. That's okay as well. It just can't hit it more than once. All right. But if all your vertical lines either hit it none at all, like on each side of the circle here, or one time, sorry, the circle is not a good example. But if it hits it either no times at all, okay, or hits it one time, talking about all the vertical lines, but as long as none of the vertical lines ever hit it more than once, then it's a function. So you look at all the possible vertical lines, you guys, all the possible vertical lines. Does it ever hit more than once? Again, it could hit it once, that's fine. It could hit it none at all, like over here. See how these vertical lines don't ever hit it at all. If it hits it one time or no times, then it is it's going to be a function. But there's a problem here. There's a problem here, right? All these vertical lines over here, they do what? They hit it twice, don't they? All of these hit it twice, so this can't be a function. You can't have any vertical lines hitting it more than once. So we say no on this one. Last one. On this one, okay, all these vertical lines over here hit it none at all, right? They don't hit the graph at all. But then when you get over here, they start to hit it what? They start to hit it one time each. One time there, one time there. You don't have to draw all these little dots here. I'm just highlighting what I'm talking about. You can see here that all these vertical lines hit the graph exactly one time, starting here and going in this direction. All the vertical lines do that. But none of them hit it more than once. None. Okay. So since all of the vertical lines either hit it none at all or one time, as long as you don't have a vertical line that hits more than once, then the answer is yes. Okay? I'd like you guys to try a few problems now. You see here at the top of the second page of section 4.6, we have some examples here. These two problems are similar to problems A and B. These two problems are similar to C, D, E, and F. Okay. Be careful with your arrows there. All right. But to hit the play button after that, and we'll talk about the answers. Don't do the these last three problems. Those are completely unrelated. But yeah, go ahead and hit the play button after you're done with problems 1 through 4, and we'll take a look at those answers. Okay. So, number 1. Again, in these first two problems, you just have to make a list because it's just a few ordered pairs. It's not a graph where you have an infinite amount of ordered pairs. It's a finite amount of ordered pairs, less than infinity. That's what finite means. And it's much less than infinity, just 3 pairs here and 4 here. So making a list is nice and easy. Domain is 0, 1, and 4, all the x's. The range is 2 and -3, all the y's, all the different y's. You don't need to list out the 2 twice, although you could if you really wanted to. It's okay. And is it a function or not? You can see here that all the x's are different. Since all the x's are different, the answer is yes, it is a function. Number 2, the domain is -5, 3, and 1. Okay. All the different x values, in other words. The range is all the different y values, 3, 4, 1, and 0. But it is not a function this time because we have a couple of different ordered pairs here, the first one and the last one, that both have the same x. 2 different ordered pairs with the same x, that cannot be a function, right? So the answer is no on that one. Let's keep going here. So moving down to the graph problems, okay, we can see here that I just highlighted what this point was. You don't have to write down 1, 0 as long as you know that it's 1, 0. I'm just highlighting that. But what is the domain here? The domain is the leftmost x value, which is 1. Okay, well, just a moment here. One thing at a time here. The domain is starts with 1 because the leftmost x value is 1. The leftmost point is right here. The x value at that point is 1, and so that's why we say the leftmost x is 1. Because we have an arrow that goes forever to the right, that means that there is no rightmost point. And remember, domain is left to right, and so the second part of the domain is the right. Forever to the right means what? It means, as we talked about before, it means positive infinity. Infinity because it's forever to the right. Positive infinity because it's pointing in the positive x direction, the same direction as the positive x values. Okay. We also have this arrow saying that it goes forever downward. That means that there is no lowest point. No lowest point. That means the low part of the range, which is the first part of the range, the low part is going to be not infinity, but negative infinity, because it goes forever downward in the negative y direction. Okay? So negative infinity is what the range starts at. Where does the range end at? It ends at the highest point, right? The y value at the highest point. This is the highest point here, okay? The graph doesn't get any higher than this, all right? And so the y value there is y equal to 0. Thus, the range goes from negative infinity to 0, low to high. Why did I say that it's a function? It's because no vertical line, you guys, no vertical line ever hits the graph more than once, does it? Okay, none of them do. And so therefore it's a function when it never hits it more than one time. Number 4. You can see here that I made my arrows here so that I know when it goes forever in what direction. All right, it goes forever to the left. It goes forever up, in 2 different places in fact. Okay, and then it goes forever to the right. The only place that it doesn't go forever is downward. That's the reason why the low part of the range has a normal number there. All the other parts have infinity in it. You just have to determine the correct sign, positive or negative. Okay, that's all because of the forever arrows. Forever to the left means that the leftmost point is negative infinity. Always means that. Okay. Forever to the right means that the rightmost point is positive infinity. It always means positive infinity. It's never negative when it's to the right. Okay? The rightmost part of the domain, that is. It's never negative. It's always positive. If it's forever. Okay? That's what makes it infinity in the first place. There is a lowest point. Why is it negative 4? It's because if we go down to the lowest point, the y value there is negative 4. Negative 1, negative 2, negative 3, negative 4. Okay? And because there is no highest point due to the fact that the graph goes forever upward, okay, that's going to be infinite. But why is it positive infinity? It's because when you go forever upward, it's always going to be positive infinity and not negative infinity, because you're pointing in the positive y values. You're pointing in the same direction as the positive y values. Okay? Why is this a function? It's because no vertical line ever hits the graph what? More than one time. Never does. Okay? And so we say yes. Yes, it's a function. Okay? All right. So that is domain and range and figuring out if it's a function or not. Now, the last part of this section is something that you may have seen before. It might be, in fact, what you normally associate with functions, and that is this symbol right here, the f with the bracket and the x inside of it. We call it f of x, okay? But, very important, especially if you're not familiar with this or you don't remember it, this does not mean f times x, you guys. I know it looks like that because the f is right next to the brackets, and normally that would mean multiplication. Okay? It does not mean that. So you might be wondering, well, how am I going to know that? Okay, how am I going to know? I mean, usually when you put something next to a bracket with nothing in between it here, in between the f and the bracket, usually means multiplication. So how am I supposed to know that this is not multiplication, but in other cases, when you put something right next to a bracket, it is multiplication? How am I going to know? Here's how you know. Whenever you have a bracket on one side of an equal sign, usually it'll be on the left side like this one is. Whenever you have a bracket with just an x inside of it, nothing else, just an x inside of it, and then you have another letter outside of it. It's usually going to be F, okay, but it could be other letters as well. It could be G sometimes. Okay, in this class, it's usually going to be F, though. F for function. Okay, that's why they use that letter. But again, if you have just a bracket with just an X inside of it, and then you have a letter on the outside of it, and that's all you have is those three things. The bracket with the X inside and the F outside. If those are the only three things that you have on that side of the equal sign, then that means function notation. It is not multiplication. Okay, that's when you know that it's not multiplication. When you have just those three things on that side of the equal sign. But because that's not multiplication, you guys, we got to be careful not to treat it as such. I'll kind of get into that more here in a moment. Okay, so what does this mean? This means this whole thing altogether, okay, it means the y value that pairs up with the x value that you're going to have in the place of x right here. For example, see how it says right here, figure out the value of f of 2. Let me write that down just to start us off. Okay, this means, you guys, that the x is equal to 2 because the whatever goes inside this bracket, that's the x. That's why it says x right here. So that 2 is an x value. But when you calculate what this whole thing is equal to, you guys, that is going to be the y value that pairs up with the x equal to 2. Okay? Because you know that with functions, it's just a bunch of ordered pairs, right? So we've got x's pairing up with y's, all right? So let's go ahead and figure this out. I'll get into that a little bit more, but let's figure this out first. How do we do that? Whatever goes inside of here, in this case it's 2, that same thing goes inside of the x's over here. So whatever, because it says x right here, if you put a 2 in here, that means the 2 has to go wherever the x is on the other side. So if I put a 5 inside that bracket, that means that the 5 has to go wherever the x is on the other side. But you got to be careful how you put it there. As I kind of talked about briefly earlier in this chapter, whenever you replace a variable with a number, you have to first of all replace the variable with an empty parenthesis. Like this. See how I'm replacing the x with an empty parenthesis, but I'm not putting anything else. I'm sorry, I'm not changing anything else. The -3 is still there, the -4 is still there, the exponent is still there, the +2 is still there, and they're all outside of those parentheses. That's why I said that parentheses have to be empty. Once you do that, then you put the 2 in there. Or if there had been a 5 inside this bracket, you put the 5 in there. Okay. Again, whatever goes inside that bracket goes wherever the x's used to be over here on the other side of the equal sign. So the x's get replaced by the empty parentheses. Then you put the appropriate number in there. Okay. Then you figure out what the right-hand side of the equal sign is equal to. Okay. Do not change this at all. This stays the way it is, you guys. Don't divide both sides by 2 to get f by itself. You can't do that. Okay. I know it looks like you can do that. It looks kind of like something like that. But remember, this is not f times 2. Remember, we said that. This is not multiplication. Okay. If it was f times 2, then you could divide by 2 to get the f by itself. Okay. But this is supposed to be all kept together as a package here. You're not supposed to separate the 2 and the f. Not supposed to do that. Keep this all together. Just figure out what it's equal to by figuring out what the other side of the equal sign is. That's all you got to do. And then you're done. Okay, they just want to know what f of 2 is equal to. Since it says here that f of 2 is equal to all this stuff on the other side of the equal sign, you just got to figure out what this is by doing order of operations. There's no variables here anymore on this side of the equal sign, so order of operations will get the job done. As you guys now know, exponents. Let me write down order of operations again here, PEMDAS. Okay, exponents come before multiplication. Multiplication comes before addition and subtraction. So we do the exponent first, like that. Then what? Then we got to do the multiplication. Okay, you got to be real careful here though, and we talked about this also in this chapter real briefly. Let me get into it a little bit more here. This is a polynomial. So when you multiply The 2, do you multiply the 2 by the 4 or by the negative 4? The easiest way to do it is by multiplying by the entire coefficient, which is negative 4. Okay, remembering, however, that this officially means right here plus negative 4x. When you have a polynomial, bunch of terms being added and subtracted together, in other words, that's what a polynomial is. If you have a negative term in the middle here, in other words, not the first term, it could be the middle term or the last term, and it's negative, remember that that's plus negative 4x. Okay, so when you do negative 4 times 2, remember you have to add whatever the answer is. I'll get into that more here in a second. Let me do this part here first. So that's negative 12. Officially, you're supposed to do the multiplication on the left before you do the one that's on the right here. There's two different multiplications here. But as you can do them both at the same time as long as you're sure that it's going to come out the same as it would have if you had done them one at a time. It will in this case, so I'm going to go ahead and just to save some space here, save a step here, do one less step. I'm going to do both of the multiplications at once. So I got negative 12, and then we're going to do plus negative 4 times 2, which is what? Plus negative 8. Now you could say minus 8. Remember, that's the same thing. Okay. You can change this to, because whenever you have a number plus a negative number, you can change that to minus, can't you? Plus negative means minus also. Okay, but I just want you to remember that you are adding the result though. Okay, you're not multiplying by negative 8, you're adding negative 8. Okay, and then plus 2. Now when you do the addition and subtraction, please remember that sometimes subtraction goes before addition. Don't be fooled by how this is written here. These two things are equal, okay, meaning that whatever comes first is what you actually do. So as you move your eyes from left to right here, you see the subtraction first and then the addition. So in this case, you do the subtraction first. Whatever comes first as you go from left to right when you're on the addition subtraction step and all the other stuff has been done, okay, that's what you do first. So negative 12 minus 8 is negative 20. And then you add the 2. The final answer is negative 18. And this is all that they wanted you to do for f of 2. Okay? They just wanted you to figure out what f of 2 was equal to. But just to let you know, okay, you don't need to write this down. In fact, this is not the answer. This is just to let you know for future reference. Okay? What we just accomplished here, the whole reason why we computed this is because we just showed that 2 pairs up with negative 18, okay, for this function. Remember, functions are sets of ordered pairs. We just found one of them. We can find more of them by plugging in more numbers. If I now plug in negative 2, I can then figure out what? I can then figure out what number goes with negative 2. And I'm going to find that out right now. But that's what this whole thing does. It figures out what the y values are that pair up with the x's that are inside these little brackets here next to the f. Okay, that's what it does. That's the purpose. Okay, that's what we're doing. Okay, so just figure out what the other side of the equal sign is equal to over here on the right. F of 2 is still just f of 2. Don't try to break up the f and the 2 there, like I said. Same thing over here. Since the negative 2 is inside of that little bracket next to the f, that means that the negative 2 is your x value right here. That means that negative 2 goes wherever you see the x value on the other side of the equal sign. So once again, put an empty parenthesis wherever you saw the x. You got to do that in order to make sure this works correctly. Okay, I promise you, especially, but not limited to negative values, but especially when you have negative values, okay, your problem's going to get all messed up if you don't use the empty parentheses. No doubt about it. It could also when you have positive numbers, but it's really going to get messed up bad. Okay, you're not even going to be close to the right answer when you plug in a negative number and you don't use those empty parentheses. Please use those anytime that you plug a number into a variable. Anytime. Okay? So then after I do the empty parentheses in the place of the x's, I then put the the x value into the place of the empty parenthesis. Now we are certain that we set it up correctly. Absolutely certain. We then do order of operations again since there's no variables here and we need to figure this out. Exponents first. Then we do the multiplication. Again, in this case anyway, you can do them both at the same time. Negative 3 times 4, again, is negative 12. Now remember again, this is what? This is, like we saw over here, this is plus negative 4x. And so likewise, after we plug in the negative 2, it's going to be plus negative 4 times negative 2. All right? What is negative 4 times negative 2? It is 8. Don't just write down the 8, though. What am I missing there? Remember, you're supposed to add the result. A lot of people will forget this plus here, and then they'll look at it and they'll be like, oh, does that mean negative 12 times 8? No, 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 no. It's supposed to be plus negative 4 times whatever you plugged in. Whenever you got a polynomial where either the second term or any term after the first term, okay, is negative, remember that it's plus negative. All right, so if you do negative 4 times whatever you plugged in, it's got to be plus whatever the answer is, plus 8, plus negative 8. But we changed it to minus 8 since that means the same thing. Okay, but plus 8 is just plus 8. There's no minus there to change it. Okay. Then we have the addition subtraction step still left. There's only addition left, so but you have to do it from left to right. No matter as long as you're on that last step right there, addition subtraction, you always do it from left to right no matter what you got. Negative 12 plus 8 is negative 4. Negative 4 plus 2 is negative 2. So what did we just accomplish again? What did we just find out? We just found out that negative 2 for x pairs up with negative 2 for y. So that's another ordered pair that is a part of this set of ordered pairs that represents this f of x function. All right? Anytime you see f of x, they ultimately are talking about a set of ordered pairs because that's what functions are. It just doesn't look like it because you don't see any ordered pairs here, right? Okay, the reason why you don't see any ordered pairs here and why I wrote it on a scratch piece of paper instead is because they just want you to focus on finding the f values. But it ultimately leads to ordered pairs, okay? And so that's why you don't need to write down the ordered pairs like I said, but it ultimately leads to that. And when you get into, in the future, when you get into some bigger function problems, you'll see that. Right now, you just need to focus on finding these f values. So please try 5 and 6 right now. You got a total of 4 values. You got to find 2 here and then 2 again down here. Find those values, hit the play button, and we'll see what they are. Okay, number 5, the first one here is f of negative 2. If I plug that in, it looks like this right here. Again, notice the x's got replaced by empty parentheses. You can't see them empty anymore. But I made them empty parentheses. The 2, the minus 4, and the plus 1, along with the exponent, they're all outside of it. Okay. The only thing that should go inside of that parenthesis that was previously empty is the number next to the f right here, because that's the x value. Only the x value should go in there. So I put the x value inside of each parenthesis. I now do order of operations since there's no variables left there. Exponents first. Remember here again, this is plus negative 4x. So when I do the multiplication step, okay, I get 8 right here first of all. But then I get plus negative 4 times negative 2. Okay, I did one step at a time here, all right. But you can do both of those at once. It comes out the same in this case, all right. But it ends up being 8 plus 8 because it's plus, and then the multiplication equals 8, so 8 plus 8. Then do the final additions here. 8 plus 8 plus 1 is 16 plus 1, which is 17. Okay, how about f of 5? Plug that in the same way we did negative 2. Do the empty parentheses first and then put the x value inside of that empty parentheses. Then you do your exponents, your multiplication. Again, I did it in 2 separate steps here, but you could do the 50 and the minus 20 all at once. Again, you have plus negative 4 times 5. That is plus negative 20. But we know that when you have a number plus a negative number, that's the same thing as saying minus 20. Okay? Then you do, remember, you got to do your subtraction here first. Do not do 20 plus 1. You will get the wrong answer. Do not do 20 plus 1. Okay, you got to go from left to right when you're on the addition subtraction step, and all the other stuff is done in order of operations before that. You know, like the exponents and the multiplication and anything else that goes before addition and subtraction. If addition and subtraction is all that's left, go from left to right. So we got to subtract first. We get 30. 30 plus 1 is 31. Okay? Number 6. And again, you don't need to write those ordered pairs that I was writing down earlier. I was just showing you for future reference mainly about why we figure out these F values. It's going to help us create ordered pairs that we're going to be able to use in bigger function problems that you see in the future. Okay? Again, that's why I wrote them on a piece of scratch paper. It's not something you have to write down. Negative f of negative 1. We put the negative 1 in the place of the x's with our parentheses, of course, as we talked about. Exponents go first. Then multiplication. Okay, negative 2 times negative 1 is positive 2 right here. Okay. And then 2 plus negative 1. Okay, same thing as 2 minus 1, because when you have 2 plus a negative, that's the same thing as 2 minus. 2 minus 1 is 1. One more here. How about if we plug in positive 1? Okay. Again, exponents come first. Negative 2 times 1 plus 1. Multiplication comes before addition. And then negative 2 plus 1 is negative 1. Final answer there. Okay, so that's how you do these function values where you have like f and then a number inside that little bracket right there. And they ask you to find that value. This is what you do. Okay, that's what we've done in the last 3 problems here, G, 5, and 6. So that concludes Chapter 4. Okay. We will be actually taking a brief trip into Chapter 3 in the next video, but for now, since Chapter 4 is over, okay, let me know if you have any questions about it, okay, as usual. But you want to make sure that as we get closer to the test here that you're starting to make sure you're understanding all the concepts, if you don't already, okay. So think about that, but in the meantime, have a good day, take care, and we'll see you back here for that brief trip into Chapter 3.